Hello, my name is Clara Meister. I'm a PhD student at ETH-Zurich, and today I'll be presenting on our work titled Determinantal Beam Search. This was joint work with Martina Forster and Ryan Cottle. So first, I'll briefly introduce the relevant background for our problem, namely the decoding of sequence models. Many of the core tasks in natural language processing involve some sort of sequence generation. For example, any one of the many language generation tasks, or parsing. Now, natural language is ambiguous. For example, there can be multiple interpretations of an input sentence, or multiple ways to phrase an output sentence. As such, there are often multiple correct answers for these tasks that a model could produce. In certain use cases, we may want to see a comprehensive set of such outputs. Let's take a deeper look at our sequence prediction models. Typically, these are probabilistic models that assign a probability to an output sequence dependent on some input. Note that we typically work in log probabilities for numerical stability, among other reasons. Now, given an input x, our goal is typically to find the highest probability output y from our set of possible outputs. This is known as maximum a posteriori inference, or less formally, the decoding problem. But like I was saying earlier, what if we want more than just a single prediction? What if we want a size k set of possible outputs? Note that we're overloading notation such that our probability mass function takes a set, where we define the probability of a set to be simply the product of individual sequence probabilities. Importantly, there's no interaction terms in this function, so our objective would be maximized just by taking the k highest probability options. Okay, so that was pretty straightforward, but what if we specifically want this set to be diverse, so that we can, for example, get a comprehensive set of possible translations for a given input? By maximizing the joint probability of a set of translations alone, is such a diversity necessarily guaranteed? Well, let's see what happens when we use standard decoding algorithms, such as beam search. Now, in sequence prediction tasks, our output space is typically exponentially large. Like in language generation, it's the set of all possible strings that can be generated from a model's vocabulary. Because today's neural sequence models are typically non-Markovian, brute force search would lead to a combinatorial explosion. So instead, we use heuristic search methods to solve the decoding problem, like beam search. Beam search can be seen as a pruned version of breadth-first search. It limits the number of paths we explore by pruning the search space down to the top k options at each turn, where k is a hyperparameter. Because of this pruning, there's no longer any formal guarantees as to whether we'll find the highest probability sequence under our model. Now, how does this change our formulation of the set decoding problem? Formally, beam search transforms our global argmax into an iterative process, where our argmax is instead taken at each decoding step. Importantly, our search is now limited to items on the beam. That is, the set of extensions of the top k items from the previous iteration. We perform this search for a set number of iterations, where this number may be, for example, our maximum acceptable sequence length. The objective under beam search is still the same as under our original set decoding problem, and as mentioned earlier, under this objective, we're purely maximizing the total probability covered by the set. Well, it turns out that in practice, this often leads to high overlap in the solution set. For example, all sentences may contain the same prefix, differing only by a few words towards the end. So, to answer our initial question, our standard set decoding setup does not in general lead to a diverse set. In the effort to address this issue, we propose a new formulation of beam search that allows us to take into account interactions between items on the beam during decoding. We call our algorithm Determinantal Beam Search. To motivate our reformulation of beam search, we first look at a base case. Let's take the recursive component of the beam search algorithm. The objective of this optimization problem can actually be reformulated using matrices and determinants. Specifically, the set that maximizes probability is also the set that maximizes the determinant of a specific matrix. That is, a diagonal matrix, where entries correspond to a sequence's probability. Note that we use the subscript notation here to indicate the submatrix of D that corresponds to rows and columns mapping to the set of items in Y prime sub T. Now, the determinant of this submatrix is simply the product of the diagonal entries, by definition, which under our proposed definition is equal to the set probability, actually. So this formulation leads to the same solution as standard beam search when our matrix is diagonal. But what if we allowed for non-zero entries on the diagonal as well? Specifically, what if off-diagonal entries encoded some sort of interaction term between respective items on the beam? How would this affect which set maximizes our new objective? It turns out that this setup leads to a diverse beam search. We can generalize our determinantal reformulation by adding a positive semi-definite matrix to our original diagonal matrix, where this additional matrix can encode, for example, the similarity between items. This then makes our new objective a diversity-promoting objective. To see why this is true, we turn to determinantal point processes. A determinantal point process, a DPP, is a stochastic point process. For our purposes, we'll look at its interpretation as a distribution over subsets of a fixed ground set. The probability distribution of this process, that is, the distribution over subsets, is characterized by the determinant of a symmetric real positive semi-definite matrix. Let's take a concrete example of a DPP, one parameterized by the matrix M, shown here. We'll take the shading to indicate the magnitude of values. Now, under a DPP, the probability that some set A is a subset of our sampled set Y is equal to the determinant of the submatrix whose indices correspond to the elements of A. For example, if our set A can be mapped to entries 0, 3, and 4 in M, then the probability that the items in A are in our sampled set Y is equal to the determinant of the highlighted submatrix. Note that by the definition of the determinant of a matrix, this probability increases when diagonal values are large and decreases when off-diagonal values are large. So in this context, off-diagonal entries encode repulsion. The higher the value, the less likely the corresponding items will both be sampled. Further, similar to our initial beam search reformulation, diagonal entries are the marginal probabilities that an item ends up in our sampled set. So what makes a determinantal point process special? Well, here's an example of two samples, each of points on a plane. Points are sampled independently in the example on the left, while on the right, points are sampled according to a DPP, for which our notation of similarity is proximity. Our notion of similarity is proximity. We can see that the sample on the right leads to better coverage of the plane, avoiding coincidental clusters. Now, when we take the mode of a DPP, rather than just sampling from it, we see that points are spread quite evenly across the plane, giving us a sample with very good coverage of the space. In this setting, we can see beam search as producing a sample like this, where points are quite clustered. So how do we make the jump from the low diversity and coverage sets produced by beam search to the high diversity and coverage ones that are the modes of a DPP? Well, that's exactly what's being done in our determinantal reformulation of beam search, which under our conditions is equivalent to MAP inference for a KDPP. That is, a DPP restricted to size K subsets. So, under our reformulation, the objective maximizing set should be both high probability and high diversity when K encodes similarities between items. One notable caveat, though, is that computing this argmax is an NP-hard problem. However, it can be approximated efficiently, for example, using a greedy iterative approach. Since beam search is already a heuristic, this doesn't really change the fact that we didn't have theoretical guarantees in the first place. Now I'll briefly show some experimental results from applying our method to language generation tasks. Let's take our matrix D to be joint probabilities of prefixes on the beam under our sequence model. And let's take K to be the string subsequence kernel. The string subsequence kernel between two sequences gives us a quantification of subsequence overlap. The higher the value, the more the strings overlap. Importantly, the matrix produced by pairwise computation of the string subsequence kernel is a gram matrix, and so is necessarily symmetric positive semi-definite. In experiments on machine translation, we can see that determinantal beam search, the blue lines, leads to sets with high n-gram diversity, as indicated by the x-axis. However, this does not seem to come at the sacrifice of median or max blue, the y-axis. In comparison, beam search with varying temperatures, the yellow lines, produces very low diversity sets. Here we have an example of sets of translations on WMT19 German to English. Each of these examples was taken from the highest diversity sample generated by the respective coding strategy, with median corpus blue approximately the same, that is within 0.02. The sets produced by beam search and even diverse beam search, another decoding strategy, have high overlap. In fact, diverse beam search even returns some repeats of the same hypotheses. In contrast, determinantal beam search appears to produce much higher diversity sets. So, to conclude, in this work, we propose determinantal beam search, a new way of framing beam search that allows us to optimize set generation for diversity and coverage rather than simply for individual scores. Formally, we redefine beam search as an iterative subdeterminant maximization problem, where we select approximately maximizing subsets, which gives us the ability to encode the notion of intraset diversity into the beam search optimization problem. We use DetBS in the context of language generation, where we explicitly encourage n-gram coverage through the string subsequence kernel. In our NMT experiments, we find determinantal beam search shows competitive performance in generating diverse sets of strings with minimal trade-off in median blue. Thank you for watching, and here's a link to our paper if you'd like further details on our work.